Hello, champions. Welcome back to another exciting ride through mathematics. Let me ask you a fun question. Have you ever cut a triangular slice of pizza right from its tip to the middle of the crust? The two sides of the pizza slice suddenly look balanced, don't they? Now imagine this with a triangle, say triangle ABC. If we pick midpoints E and F on sides AB and C, and then join them with a line, that line EF turns out to have some magical properties. It behaves just like a mini version of the base BC. This discovery is what we call the midpoint theorem. And believe me, it shows up in everything from folded paper crafts to cricket fields. Here's the heart of it. Theorem 8.8. It says, the line segment joining the midpoints of two sides of a triangle is parallel to the third side and its length is half of it. In symbols, if E and F are midpoints of AB and C, then EF parallel to BC, and EF equals 1 by 2 into BC, picture the cricket pitch. If BC is the full 22 yards, then EF is like a mini pitch, just 11 yards, but perfectly aligned. Or think of drawing a scaled-down copy of a base line on graph paper, same direction, half the size. That's the beauty of this theorem. Now here comes the reverse play. Theorem 8.9, the converse. It says, if you draw a line through the midpoint of one side of a triangle parallel to another side, then it automatically bisects the third side. So if E is the midpoint of AB and EF is drawn parallel to BC, then F divides side C into two equal halves. That means AF equals FC. It's like clipping a triangular towel at one midpoint and stretching a string parallel to the opposite side. The other side of the towel balances itself right in the middle. This converse makes sure the theorem works both ways, forward and backward. Alright, but why do we love this theorem so much? Let's explore. First, it helps us detect hidden parallelograms inside triangles. Connect midpoints and you suddenly see a tiny parallelogram appear. Second, it divides a triangle into four identical smaller triangles. Imagine you and three friends sharing a sandwich, equal parts, no fights. Third, it is a powerful shortcut in coordinate geometry. Just check slopes. Slope of EF equals slope of BC, done. And finally, it proves fairness when parallels cut across transversals. Equal intercepts appear like magic. No cheating allowed. That's why this theorem is a favorite in both pure geometry and algebraic proofs. Let's try a real exam-style question. Suppose we have three parallel lines L, M, and N. They are cut by two transversals P and Q. On P, the intercepts AB and BC are equal. We need to prove that on Q, the intercepts DE and EF are also equal. Here's the plan. Join A to F, forming trapezium is CFD. In triangle ACF, B is the midpoint of AC, and BG is drawn parallel to CF. By the midpoint theorem, G is the midpoint of AF now. In triangle AFD, with G already the midpoint, line GE parallel to AD forces E to be the midpoint of DF. Therefore, DE equals EF. So the intercepts cut off on one transversal are equal, and automatically, those on the other transversal are equal too. Think of this as two railway tracks being cut by two footbridges. If one bridge divides the space evenly, the other has no choice but to follow suit. So, let's gather the wisdom from today. The midpoint theorem says, the line joining two midpoints of a triangle is parallel to the third side and half as long. Its converse guarantees that drawing a parallel through a midpoint forces balance on the opposite side. Applications? Loads, hidden parallelograms, equal divisions, coordinate proofs, and equal intercepts with parallels. In short, triangles love balance, and the midpoint theorem is their secret recipe for it. Next time you fold a napkin or share a piece of cake, you'll see this symmetry in action. And with that, we close today's chapter. In our next video, we'll unlock more exciting properties of quadrilaterals that build on this foundation. Until then, stay curious, keep practicing, and remember, geometry is everywhere, from pizzas to playgrounds.